In today's lesson, we're going to talk about capacitors. Now, before we start, I got to tell you, we could do an entire course on capacitors, so we're just going to be like a rock skipping across the surface of some water here today, just hitting on the highlights of capacitors. And you're going to come back and see capacitors in several more classes before you're done here. So for now, let's just learn a little bit about capacitors, and then we'll sort of plant the seed for future learning. So a capacitor is a device that allows charge to accumulate on two parallel plates. It is also the very first device that we've seen that is explicitly time-dependent in its behavior. We're going to see that the equations that control capacitor behavior are differential equations. They're equations that involve derivatives because capacitors require calculus to fully understand. So that's something to be aware of, is that we're going to be working with differential equations for the first time in this course. So this is also going to represent the beginning, not the end, but the beginning of the transition from constant quantities, DC or direct current quantities, to time-dependent quantities, also referred to as alternating current or AC quantities. Here we have a very simplistic picture of a capacitor that I've drawn. You can see that up here we have a metal plate, and down here is another metal plate, and in between I've just shown a gap. Now that gap could be filled with a vacuum. I guess it wouldn't be filled with a vacuum, there would be a vacuum between the plates. It could be filled with air, or it could be filled with a solid or liquid material that would serve as a dielectric. Dielectric is just a fancy word for the insulator that's going to be between those two plates. Now what happens is that if you apply a voltage to these parallel plates, current is going to flow. Current will flow from the bottom terminal to the top terminal, and usually this doesn't matter, but in this case it does. As the current is flowing in the sort of clockwise direction, actually the electrons are flowing in the counterclockwise direction, because remember, the electrons have a negative charge. So the electrons are flowing away from the top plate and they're flowing onto the bottom plate. Now there's a gap here. They can't go between the two plates. They would love to be able to make a complete loop. But what happens is it's sort of like if you go on a vacation, but you end up at the neighbor's house rather than coming back to your own house. You start on the top plate, you go all the way around through the voltage source, you come in on the bottom plate, and then you have to stop there. So you're leaving behind a net positive charge on the top plate, and you're accumulating negative charge on the bottom plate. That's what happens with a capacitor. Now the amount of charge that's accumulated can be calculated. We can calculate how much charge is going to be on the top plate, and the exact symmetrical charge is going to be on the bottom plate, but with the opposite sign. We know that because it turns out that the charge is proportional to the voltage that you apply. If I apply 1 volt, I'll get a certain amount of charge. If I apply 2 volts, I'll get double the charge. And you might say, well, how can you calculate that charge? Well, that's going to simply be the ratio of charge to voltage is going to be defined as the capacitance. So we can say charge and voltage are proportional to each other, and we're just going to choose C to be the constant of proportionality. C is the symbol that represents capacitance. The unit of a capacitor is farad. It's named after another physicist. So the farad is actually a very large amount of capacitance. I don't believe I've ever held a 1 farad capacitor. Maybe I have, but they would be like the size of a Coke can, if not larger. Most of the time, we're going to be working with capacitors that are much smaller, on the order of microfarads or nanofarads. So we're talking about relatively small capacitors. And although this is the fundamental definition, equation 1 is the fundamental definition of C, I usually tend to remember it as VC equals Q. And the reason why I remember it that way, and you can see if I multiply both sides of equation 1 by V, I would get equation 2. The reason why I remember that as VC equals Q or CV equals Q is that it rhymes. So CV, VC, those rhyme, and Q, which doesn't rhyme, appears on the other side. So that one's easy to remember, so you don't have to look it up in a textbook every single time. It turns out that we can calculate the capacitance then if we know both the voltage and the charge. Usually we will know the voltage, but usually we don't know the charge. It's actually quite hard to directly measure charge. So what we'd like to be able to do is calculate the capacitance, measure the voltage, or apply a fixed voltage, and that will allow us to calculate the charge. We can calculate the capacitance if we just know 3 things. We need to know the distance between the two plates. We need to know the area, the surface area of either plate. They're going to be identical to each other, but don't add the two surface areas. So if this top one is 1 square centimeter, then the bottom one is also 1 square centimeter, and the value of A is 1 square centimeter. We also need to know something about the material that is between the plates. Now, it could be a solid, it could be a liquid, it could be a gas. Most often, it's going to be a solid. But this epsilon sub r here. That's going to represent the dielectric constant. Actually, epsilon sub r is the relative dielectric constant. We need to multiply that epsilon r by a constant epsilon 0. Epsilon 0 is the dielectric constant of free space, the dielectric constant of a vacuum. So epsilon r is saying how much better of a dielectric do we have as compared to if it were just left as a vacuum between the two plates. So we take the epsilon r times epsilon 0, we multiply that by the surface area, and we divide it by the distance between the two plates. And the value of epsilon 0 is shown here, 8.85 times 10 to the minus 12 farads per meter. And the value of epsilon r depends on the material. I've listed here several common materials and the corresponding relative dielectric constant that would correspond to each of them. Notice that for the vacuum it's defined to be 1, because after all epsilon 0 already includes the full effect of a vacuum, and air is so close to a vacuum that we will always just use 1 for air. But I wanted you to know that the actual correct value at standard atmospheric temperature and pressure is 1.00059. You should just always use 1 if I tell you that it's air between the plates. Glass can vary depending upon the characteristics of the glass between 5 and 10. We have mylar, polyethylene, neoprene, germanium, and water. There are many other types of materials. By the way, notice how large the dielectric constant for water is. That's because the dielectric constant depends on how polar the material is. And water molecules are among the most polarized molecules that we know of. Now, almost no capacitors use water as their dielectric because it's really hard to keep the water in there. So ordinarily the water would just sort of drain out, and so it doesn't work well. We almost never would use liquid as a dielectric constant. We'll almost always use a solid, which means glass, mylar, polyethylene, neoprene, or germanium, or one of several other materials. There are some highly engineered materials that can yield some very, very high relative dielectric constants, which will in turn give you higher values of capacitance. So those are just some good things to know. If I gave you the information about epsilon r, or even about the material that's being used, and the geometry of the capacitance, A and D, then that would allow you to calculate the capacitance value, which would in turn, if I also told you the voltage, would in turn allow you to calculate the charge that's appearing on either one of the capacitor plates. So I think you're ready to do some of those example calculations. So I'm going to go ahead and set you loose on the calculating capacitance example problem.